Hey, this is Mr. Mitchell with a video. This one's going to be on fundamental frequencies and seeing colors later on in the video. Why does an A note on a piano sound differently than an A note on a guitar? Well, it's because of a couple of things we've touched upon, but we want to go over a little bit more. Fundamental frequency and harmonics. Fundamental frequency, you may remember, is what determines the pitch. You can take like a tuning key and hit how it is supposed to sound like whenever you have an A, and then adjust it with the strings in the back to make it sound like that tuning fork, I think is what it should be called. So that fundamental frequency is what you get as how it's supposed to sound. That's the same thing you do with a guitar. You kind of have how it's supposed to sound, but the fundamental frequency is different for different instruments. Um, the harmonics is a little bit harder to understand than fundamental frequency, but it has a lot to do with it. Harmonics are the whole number multiples of the fundamental frequency. For example, if you have the A played by one of these two, it might be at a 110 hertz. If you have one octave above it, it is 220 hertz. One octave above that is 330, an octave above that is 440, an octave above that is 550. It can go on for a long time. Notice that's what harmonics are, whole number multiples of that fundamental frequency. Have you ever noticed, for those of you who have played the piano, if you take an A over here and then go 7, 8 notes down and play the A over here, that it kind of sounds like it should. The A down here sounds, well, kind of like an A up here sounds. It just has a higher pitch to it. And if you play the A and play the A here, they sound more together than if you say play the B and play the A at the same time. They have some kind of harmony to it, and that's probably why they ended up having the term harmonics in the first place, because it does seem to fit. So when you have this 220 hertz, it's another harmonic of the 110 hertz. It's another harmonic here, another harmonic here, another harmonic here. They are the whole number multiples. And what happens pitch-wise, of course, the more harmonics you end up playing, the higher the pitch, and every octave up you double in the frequency. So it's frequency. So if you have the sine curve, if you go up one octave or one harmonic, you will have double the numbers of up and down you would have in the 110, and then double the number for each little octave up, you might say. Just as, let's take a look at this. Oh, something I haven't gotten to yet. Here I have the harmonic series that I found online. You have first harmonic, second harmonic, third harmonic, fourth harmonic. Notice what you have here. These are standing waves. These are standing waves with a node right in the middle. The antinodes are all around there. These are standing waves. And what you have is, for every harmonic, you get a node in there, and the harmonic plays the high frequency part in the antinodes. So what happens is you kind of have a bit of constructive interference that's going on here. You are playing the A that kind of is in tune, I guess you might say, with the upper A. Mention the word octave. By octave, here's what it would be on the piano. It is like the 8th note up every single time, and that would be the harmonics for, in this case, C. Just like different notes have different frequencies, different colors have different light frequencies. Let's shift gears to colors. Now we have already talked a little bit about colors. But I kind of want to touch on something that we didn't really have time to hit very hard. When you see light with a wavelength of about 550 nanometers, your brain interprets it as green. But the leaf doesn't emit green on its own. If you were to turn the lights out on this picture, you wouldn't see any green glowing. You wouldn't. The leaf doesn't emit that light. So where does the green come from? Just to see light, it kind of, well, it's hard to believe that this green comes from the multicolored visible spectrum that we have. But you see what we have over here. We have what's called white light. It has every single color of the spectrum in it. So when that white light hits this background, the red backdrop, what happens is all the colors except red are absorbed, and the red is what's reflected. Same thing here, all the colors except blue are absorbed, and it's the blue that is reflected. All the colors here that are hit except green are absorbed, and the green is reflected. And the red, the blue, the green have different wavelengths. The green happens to be about 555 nanometers. So when all that sunlight hits here, the leaf is going to absorb every color except the green, and when it bounces off and comes to our eyes, what we interpret that frequency in is green. Look at this woman right here. All the colors are going to come from the sun and hit these flowers. They absorb every color except the red, and the red is what goes to her eyes, and the eyes correctly interpret it as red. So light contains all the colors, just like you were using a prism, you can see them all. The white light strikes the leaf. The leaf reflects the light with the correct wavelength. The rest of the colors are absorbed. When the light is reflected to you, your brain interprets it as green. If you were to view the light, if you were to view this leaf under a red light, that means it does not have all the colors, it just has red. What color do you think this leaf would show up as? It would show up as black, because there is not a green. Normally there is a green amongst all these lights, but if you have nothing but a red light coming in, there is no green in there. Now what would happen to the rose part? Yeah, it would show up red because it reflects the red. Televisions and computer monitor displays have many colors. They display all kinds of colors by combining the light of the additive primary colors. Here are the primary colors, red, blue, green. Adding light of two of these colors can produce secondary colors. If you have red plus green, you make yellow. If you have blue plus green, you have a teal-like color called cyan. Here you have magenta when you have blue and red. So the TV and colored monitor displays for computers kind of take advantage of combining colors. Mixing all three colors makes white. In the reverse process, pigments, paints, or fillers of the subtractive primary colors, that's the yellow, cyan, and magenta, these are the ones that were in here, and there's the subtractive colors, primary colors. If the filters or pigments of all three of these colors combine in equal proportions, the light is absorbed, leaving black. And black, of course, is an absence of color. Well, I hope you learned a little bit about harmonics and seeing color.